Hello guys, welcome back. Today we'll be solving the problem of the section F problem 15. I'm not sure whether this is aligned with the problems of the real question paper, but I think the what we have planned is that we have done the solution much before the actual question paper came out. So I'm not sure about this whether it matches with the actual question paper or not. But let's get into the problem very quickly. This problem is a bit interesting, but also it demands some remembering of certain results, which is not good, I think, for an exam, because these results are not really easily. I mean, these results are not really easily rememberable, so it cannot be easily remembered. Anyways, let's get into the problem. So x and y are standard normal random variables, and which of the following x, y, z equal to mod x by mod y? Which of the following expectation is finite? If you think about this problem, you must first always think like what do you know about similar to such statements. So what we know is that x by y follows Cauchy. We know that x by y follows Cauchy, and Cauchy doesn't have a finite expectation. Okay, Cauchy doesn't have a finite expectation, and since Cauchy doesn't have a it doesn't have a finite expression, it has infinite mean, and therefore observe that z, that is mod of x by y, is greater than equal to x by y, right? So its expectation will always greater than also. Okay, that makes a lot of sense. So therefore expectation of z is also infinite. Okay, so expectation of is also infinite. The next one is that let's try to understand certain property, that the exchangeability property of the random variable over here. So what is the exchangeability property? Since x and y are independent standard normal, therefore y by x is also independent standard normal similarly. So essentially if z, the distribution of z and distribution of 1 by z is always similar. In fact, distribution of z to the power k and distribution of 1 by z to the power k is always same, because x to the power k by y to the power k is modulus is same distributed as y to the power k by x to the power k, because of the exchangeability of the random variables. That is, they can be independently used to make the same distribution. That makes sense because they're independent random variables. So therefore, 1 z to the power k is follows z to the power minus k also. Same, right? The distribution is same, so the expectation will also be same. The expectation of z to the power k is same as expectation of z to the power minus k. So from here you can understand, since it's I'm just telling you the keys of solving MCQ problems a bit, is that this is z to the power 3 by 2, right? So this is z to the power minus 3 by 2. So therefore expectation is same. So if this was the answer, if this was finite, okay, then this would have been finite too. So it was a multiple choice. So it's not that case, right? So therefore we have that this is also, this is not true actually, I should say. This is not true. So these are false. Okay. Uh, Also you can calculate from here why it's not true, but we need to know a result, so therefore it must be true. Okay, but to make it mathematically more compatible, more rigorous, um, the thing is that, can you first of all prove that z to the power 3 by 2, okay, the idea is that z to the power 3 by 2 is greater than equal to, or is it greater than equal to z mod z? No, because it depends upon the sign, if z is greater than 1 or z is less than 1. Okay, but z to the power 3 by 2 is surely greater than, no, I cannot really tell that in the positive version. No, we cannot really tell that. So we cannot really tell that when it is really infinite or finite, but I mean, what we know about that, so that can be a regular subjective problem for you to understand why z to the power any k, where k greater than 1 is not a finite random variable. Okay, not finite random variable is wrong word, is not, why it doesn't have a finite expectation. So you can use the results and inequalities to prove that. But what result do we have over here is that if z, module of z of the modulus of Cauchy 0 1, standard Cauchy 0 1, uska p whole to the power p, where p is less than 1, less than 1 greater than minus 1, that is modulus of p is less than 1, which has a distribution, sorry, its expression is sec of pi p by 2. Like if you put p is equal to half over here, we get that it's sec pi p by like pi by 4. So you know that what the value is. So it's finite. So using this value, we can understand and do the result. But is there no to solve the question in the exam? We didn't need this result. We just need this extensibility property and the basic inequality. So I think they have given this question with like keeping that in the mind. Okay, not a subjective problem. So yeah, but sometimes these problems remains results are helpful, but I don't think it's not required in the exam. Okay, so this is it, and it is a really interesting problem, and the idea is really beautiful. How to solve the problem? So yeah, so see you in the next video, and don't forget to subscribe to our channel, and don't forget to comment your views or your way of proving, and don't forget to hit the bell icon to get the fastest notification. All the best, and I see you in the next video.